one, how much greater than the other one. So what would I come up with? There are cases where I come up with ratios, but it's a little bit more difficult to interpret that. It's easier to interpret if instead of a ratio I take what? These are already percentages. So what I want to do is I'm going to have to take just the difference. You guys are making it too hard. Now, how many of you thought difference right to begin with?
I thought that was a little bit too simple to be the right answer.
Right. Most of you thought that. You thought it was too simple. Well, it is that simple. You're just going to take the difference. So we're going to look at the difference between P1 and P2. Now, get in the habit of putting the parentheses around here because we want to treat this as one number. This will particularly keep us from getting in trouble when we calculate confidence intervals. So, if this is the parameter, what's the estimate? Remember, it's simple. If the parameter is P1 minus P2, it's just the difference between these P hats up here. P1 hat minus P2 hat is our estimate. What's the next thing in our table? Standard deviation. Now, when we write this out, it looks nasty. It's really just the same thing as we had over here. Originally we had P, now we got a P1 and P2. Originally we had this standard deviation for the single proportion. All we're going to do is add a copy of it in for the second proportion. So what we've got is P1 times 1 minus P1 divided by N1 plus P2, 1 minus P2 divided by N2. That's all it takes. So that tells us enough to come up with the sampling distribution for this estimate. Just like we had for the single proportion, it's going to be normally distributed. If our samples are large enough, we'll talk about that in a second. It's going to be centered at P1 minus P2, and this will be the standard deviation of that bell curve. So if we calculate P1 hats minus P2 hats for a number of samples like this, their distribution will look like a bell curve with this center, and it will be spread based on this standard deviation. This is also why I'd rather you get into the habit of writing the numbers into the formulas before you calculate, because the probability of this coming out wrong is even higher than the previous ones.
Is that for all confidence intervals?
We're not going to be able to use this for a confidence interval.
Oh.
That's the next column.
Standard error.
We're going to need a standard error. So what should I do for standard error?
Same thing with P hat.
Essentially the same thing, yeah. This is the same thing except we have a P hat in place of the P's. And what I'm going to do is I'm just going to write it as P1 is equal to P1 hat, P2 is equal to P2 hat. That way I don't have to write the whole thing out because I'm going to write it out in a second anyway. So all we're going to do is just stick that value in there. What's the next thing in our table? Multiply. A multiplier for this, we have a normal distribution. It's going to be the same as we had for the single proportion case. It's just going to be Z star. The values of Z star are identical to the ones that we had for the single proportion case. So we've got 1.96 for 95%, and whatever else the others are. I can never remember them off the top of my head. I think it's 1.64 for 90%, so forth. So if we want a confidence interval, we have an estimate, plus or minus, multiplier times standard error. We have all the pieces we need to create that. So our confidence interval then is P1 hat minus P2 hat plus or minus Z star, the square root, P1 hat, 1 minus P1 hat, N1, plus P2, there it's just a matter of plugging the numbers from your problem into the appropriate places. Calculate your interval.
For the different confidence intervals, you just put in the appropriate number for each side, right?
Correct. So the only thing that changes to go from a 95 to a 90 to a 98 is a different value of z star. The standard error will remain the same for each case. Standard error will tend to change from sample to sample, but not going from one level of confidence to another. Okay? So we have everything we need for confidence intervals. The rest of our inference is hypothesis test, right? So if we do this, let's start over here. Step 1 of our hypothesis test is the hypotheses. Our null hypothesis is always a parameter plus or minus a null value. So a parameter equal to, and what would our null value be in this case? What makes sense to put right here? Remember that our hypotheses are always about population parameters. We never have sample values in hypotheses. So if I'm comparing P1 and P2, one of the things we said a moment ago is we'd like to know if they're equal or if one's greater than the other, things like that. So what would you put for this value?
It'd be 0.
It's just 0. And then we would have P1 minus P2 either less than, greater than, or not equals. Same null value. So the null value down here is 0. There are rare cases where that null value could be something other than 0, but those are very rare cases. I very seldom see it, and you will not see it in this class. How else can I write that null hypothesis? Anybody read this section ahead of time? How else would you write that? If I didn't write it that way for you up here, what would you have put down? How about just P1 is equal to P2? That's all that null hypothesis is that P1 is equal to P2. By writing it this way, though, we keep it in the same template form as everything else that we're working with, and so we can kind of plug and chug through our process. You'll see in the textbook in a lot of cases, it will put P1 is equal to P2. You'll also see P1 less than P2, P1 greater than P2, and so forth. So you'll see the relationships. Those are exactly the same as what I have here. All I've done is just reorganize things so I still have that null value in place of it, so we can look at how that works.